Hello everyone and welcome to episode 5 of the Core of Everything, where today we're looking at meteorites, asteroids and comets and etc. It's estimated that nearly 50 tons of meteoritic material arrives in Earth's atmosphere every day and 17,000 fall to Earth every year.
Yeah, and these numbers are actually really interesting because they are so hard to work them out, because meteorites that are bigger than sort of, I don't know, a couple of centimetres, maybe you can find them, but a lot of meteorites fall in places where we're not looking, so the oceans or deserts, including Antarctica, yeah, exactly. And then you get lots of small meteoritic material as well, which we might talk about in a future episode. So it's really hard to estimate this stuff, and actually this might make it sound like the Earth is getting bigger over time because we have all this material arriving at the Earth from space.
Or heavier.
Heavier, yeah, exactly, yeah. But actually we are also losing material from the Earth's atmosphere. So in a Scientific American paper in 2009, they predicted that we're losing 3 kilograms per second of hydrogen and 50 kilograms per second of helium. Now this is being lost from the atmosphere as these kind of molecules or atoms get enough energy just to fly off into space.
They're the lightest elements on the periodic table, aren't they? So they would just float away.
Yeah, and that's why we lose more hydrogen than helium, because hydrogen's lighter. So actually it's not just a case of getting heavier, we're losing material as well as gaining stuff.
Yeah, exactly. And it became apparent that last episode I didn't really know the difference between all these different things like a meteorite, meteoroid, that sort of thing. So I think it's important to establish that. So the first question that we should start the episode with is, what is the difference between a meteor, an asteroid and a comet?
Yeah, so let's start with our asteroids. So asteroids are basically small rocky objects that rotate or orbit the sun. And some of them do rotate as well, actually, on their own axes. Now, when I say small, some of them are very big, some of them are not so big. But these are basically thought to be the leftovers from the solar system building process. They're kind of the planetary building blocks, effectively. I don't know if you've built any Lego at all.
I have in my time when I was sort of 8 or 9. It was huge, wasn't it, at the time?
Yeah, still is.
Sorry.
But when you build your Lego kit, you put all the pieces together, and you get to the end, you have the finished piece, and then you look down on the table, and there's that one piece left over. And that's actually a really good analogy for what's going on in the solar system. We've built all our planets from these various components in kind of this cloud of dust and gas. And after they've been built, there are leftover pieces, and these are our asteroids. And then we also have our comets. So our comets are balls of ice and dust that are orbiting the sun. And our comets act a little bit differently to asteroids. Asteroids are on, let's generalise, we'll say they're on a fairly circular orbit around the sun. Whereas our comets are actually on highly elliptical orbits typically, which means they travel really, really far out and then come in very close to the sun and then go really, really far out the other side.
But they're typically easier to see, right? Because their orbits take them close to the sun, it gets hotter, and because comets are made of ice and dust, they vaporise.
Yeah, absolutely. So we all know that comets have tails, and actually comets have 2 tails. So they have a tail of ion gas, and this points away from the sun, and we see it through the ionisation of various gases in this tail. And this points away from the sun because these gases that are being lost and ionised, they are interacting with the magnetic field of the sun, and so they're basically channelled outwards away from the direction of the sun. And then we've also got the dust tail of the comet. So our comet is shedding material, and this is kind of more driven by the direction that the comet is moving in, but it does get curved by various other processes in space, such as interaction with the solar wind.
Yeah, we have visited a comet before, haven't we?
Yeah, absolutely. We had the NASA Stardust mission, which flew through the coma. So the coma is just kind of this sort of fuzzy, tenuous atmosphere of material that we're losing. We say that material is sublimating. That means it's going from a solid to a gas. So an example that you might have seen on Earth is dry ice, so solid carbon dioxide. That typically sublimates, so it skips over that melting into a liquid phase and goes straight to a gas. So our Stardust mission actually flew through the coma, the tails of the comet Wild 2. It came within about 237 kilometres of the comet. So it sounds quite far out, but the comet itself is 5.5 kilometers in size. That's the nucleus of the comet, the actual kind of ice and dust part. And this mission had a cosmic dust flux analyzer to work out how much material the comet's losing, as well as a mass spectrometer to look at the compositions of various things, and also a sample collector made of something called aerogel, which is like a really low density sponge that allows you to preserve the material that's coming off the comet. So if you had like an aluminium plate, when your comet particles collide into that, they're going to get changed, basically.
Okay.
They might melt a bit on impact, for example.
Okay, so it just preserves these tiny little particles of dust.
Yeah,
and ice.
absolutely. And we have actually also landed on a comet. So the European Space Agency mission Rosetta sent the Philae lander to comet 67P, which is...
How do they come up with these names, by the way? What is that?
So the naming of comets can be a little complicated, but typically they're named after the person or the spacecraft that was...
Colin the Comet or something.
That would be nice, wouldn't it?
Yeah.
Of the person on the spacecraft that discovered them. So an example is this one that the Rosetta mission visited, and it sent the Philae lander down onto the surface, which is really cool because we were actually able to kind of look at things up close, see what processes we have that are removing dust from the surface, what the surface activity is, what it's made of. We saw water, ice, and various complex organic compounds. But this comet that we visited, it was called 67P Churyumov-Gerasimenko. Apologies if I've not quite got the pronunciation there right.
It rolls off the tongue.
It does. So it was discovered by two people called Klim Churyumov and Svetlana Gerasimenko. And the P just means that it's a periodic comet, so we know it's going to come back at some point.
Okay. And then we have meteoroids then that are small pieces of a comet or asteroid. Is that right?
That's right. So as these rocky bodies in space crash into each other, we break off little pieces, and these are called meteoroids. And the way that I remember that is that the meteoroids are out in the void of space. So that's before they come anywhere near Earth. They're called meteoroids.
Okay, that's good. That's a good rule of thumb. So they're out in the sort of void of space, but where do all these things come from? So where does the asteroid belt, for example, where does it come from? How did it form? You know, I know that we see in textbooks that it looks like this thick belt in between the rocky planets and the gas giants like Jupiter, but actually it's not like that at all, is it? It's quite thin, and the spacing between these asteroids are substantial.
Yeah, our asteroid belt is really dispersed. Actually, if you stood on an asteroid, you probably wouldn't be able to see the next closest asteroid. So it's very different to scenes like in Star Wars when Obi-Wan's chasing Jango Fett through this kind of clustered
darting in and out of asteroids.
Exactly, or Han Solo landing on an asteroid. It's actually quite different. And that means because our asteroids are quite dispersed, and we think they formed in different areas of this kind of early solar system, they probably have different compositions, which we'll come on to a little bit later. But these meteoroids are sourced from a few different places. We think that they come from the Moon, Mars, as well as mostly from the asteroid belt. And so most of these bodies are further away from the Sun. We'd say they have a greater heliocentric distance. That just means they're further out into the solar system. And that's because things like to spiral in towards the Sun. It's not just gravity that affects that. There's a few other things that particularly affect smaller meteoroids and micrometeoroids. And so they're gradually drawn in over time.
So they're drawn into this asteroid belt? Is that what you mean?
Towards the Earth.
The Earth.
Yeah.
Okay. So they're drawn into the Earth, but they come from this asteroid belt, which everyone thinks is all these different rocky or bodies that, you know, it's, from a textbook it looks substantial, but actually the total mass of this region, this belt, is 1,000th that of Earth, and a single asteroid, which is Ceres, they pronounce that right?
Yeah.
Comprises a third of its total mass, and which is now classified as a dwarf planet. But how did this belt come to be?
Yeah, so we've got all this material out there, but there's a huge variety in the sizes of things, and as you've said, Ceres comprises a large amount of the material in the asteroid belt. But the main theory is that in our early system, we had our kind of early sun that was forming, and it was surrounded by this disk of gas and dust called the protoplanetary disk. And over time, things started to stick together. And there's a few theories about how that might have happened, such as kind of turbulence within the disk. Stuff sticks together, and then we get gravity kind of snowballing to form our planets. And they formed from smaller objects called planetesimals, which are probably similar to objects like Ceres and our asteroids. So you could almost call these objects failed planets, or more like the building blocks of our planets. And these materials vary with distance from the sun. So the closer in, we can have things that are more stable at hotter temperatures, like rocks. And then as you go out, you get your gas giants. And then we also have our ice giants, which form beyond the snow line. And then the leftovers from this planet building process, we get our asteroids.
Okay, so by the way, I'm aware this is a very Mark dense, heavy episode, but this is your remit, and I don't know a lot about this.
And there are people who know much more than I do as well.
No, well, you're pretty competent. Sorry, mate. But so we have to summarise, this asteroid belt is comprised of the rocky bodies that are found closer to the sun and the ice bodies that are further away. And examples of this are Ceres and Vesta.
Yeah.
And these are two vast asteroids.
Yeah, exactly. So the Dawn space probe visited some of these objects and looked at Ceres and saw that it is rich in ice. And that means that we think it formed further out in the solar system where it's colder. In the solar system, we have something called the snow line. That's basically the point where water exists as ice further out. And it's possible that objects beyond that are going to have ice on them, and then maybe they'll transition and actually move in closer. And the snow line will move as well, depending on the activity of the parent star, or in our case, the sun. So we think Ceres formed a little bit further out and then maybe was dislodged by some of the larger planets by their gravity or orbital resonances, which is basically like stable orbits due to all the objects in the solar system, and then inserted into the asteroid belt. Whereas Vesta, we think it's a little bit smaller than Ceres, but it has a different composition. It's much more like the rocky worlds of the inner solar system. And actually, some of these larger objects, such as Vesta, have undergone differentiation. So we talked about that a little bit in episode 2, in the Earth's interior. This is when our layers start to separate out. And you can only do this when objects are big enough and have enough internal heat.
Yeah, okay. So that's that differentiation, and the asteroid belt itself is kept in place by orbiting the sun, but also the gravitational effects of Jupiter, I think.
Yeah, and sometimes things do get pinged out. So it's possible, we're investigating this in the coming years, but it's possible that the moons of Mars, Phobos and Deimos, are actually asteroids that got pinged out of the asteroid belt and inserted into Mars's orbit.
Oh, very cool. But how do you get pinged out? For collisions? Or?
Yeah, I mean, lots of different reasons. It could be subtle changes in these orbital resonances, for example.
So these things that are pinged out, we'd call them meteoroids because they're travelling through space out in the solar system.
So in the case of Phobos and Deimos, they're still asteroids.
Oh,
but then,
I've got it wrong again.
If they are... when you have collisions of asteroids and you produce smaller little bits of rock, these are then our meteoroids.
Okay, so you have meteoroids that are travelling through space, and then we have meteors that are falling down to Earth, that have that streak of light as it goes through our atmosphere. So shooting stars.
Absolutely.
And most of it breaks down in the atmosphere, but the bit that
vaporized.
doesn't, that hits the Earth, is called the meteorite.
That's right. And meteorites, the way I remember this one is that they are right in front of us because they're on the ground.
Yeah.
At our
And
feet.
meteors because they're awe-inspiring.
Nice. Oh, brilliant. I've always...
Or inspiring. Am I right? High five? Right, I'll come over. High fives.
I've always looked for something to help me remember that one, so I'm really grateful that you've actually found that for me.
Yeah, by hook or by crook, we found it.
But you're right. So meteors, shooting stars coming through the sky. Sometimes, typically, our meteor showers are actually when we pass through the tails of comets. Yeah. So they're related to comets rather than bits that are broken off asteroids. And then we also have our meteorites. They burn bright in the upper atmosphere and then move into the dark flight phase where they're not burning up anymore and it's just a rock flying through the atmosphere. But there's a few different things that can happen two are meteors. If they're really, really bright, they can be called fireballs.
I love that.
It's great, isn't it?
That's so good.
It's so good. And
Chinese
then
fireball.
if these fireballs explode, we'd get an air burst, and these are then called bolides. And actually, there was a really big one about 10 years ago over a place called Chelyabinsk in Russia, and there was this massive...
that was a trending video online.
It was.
Wasn't
So
it?
it was caught on a lot of dash cam footage,
Yeah.
and like doorbell cameras and
remember
things like
seeing
that. And it injured about 1,200 people. So they weren't actually injured from the impact itself. It was more due to the shockwaves from the impact. So things like smashing glass, for example. And then a really cool one, a really cool meteorite actually, or cool for us, but not for the person that it affected, is the Hodges meteorite. So this landed in 1954. It was an H chondrite, which we'll come on to talk about in a little bit. But the reason it's called the Hodges meteorite is because it actually hit someone called Anne Hodges. This is in Alabama where this happened. I've actually held this meteorite. It's an amazing chunk of rock.
How's Anne doing?
She was actually okay. So she was asleep in the chair, came in through the roof, hit her radio, bounced off the radio and hit her in the leg. And she was okay. There's a picture of her kind of lying on the bed with loads of people gathered round because they all flooded to this area. It actually caused a huge lawsuit because people weren't sure who it belonged to, whether it belonged to her because it hit her. They were only renting, so whether it belonged to the landlord or whether it just belonged to the state or the US in general. But one thing I want to highlight here is that meteorites, we have falls and finds. So finds are meteorites that we come across that we've not seen them come through the atmosphere. You know, you're walking through the park and you find a rock and it's a meteorite. That is a find. We also have falls. Falls are meteorites that we've observed have happened, either by seeing it land and then running after it, or using kind of videos or orbital imaging and seeing where they've landed, and then we go out, chase after them and pick them up. And they're better because we know exactly where they've landed, we know when they arrived, how long they've been out, kind of sitting around on the Earth's surface.
Can you tell, it's a bit of a side point, can you tell what kind of meteorite it's going to be based on the streak of light it produces in the atmosphere?
That's a really great question. From my little understanding, you kind of look at these streaks of light and think, oh, it's just a streak of light. But actually, there is a lot that you can understand from them. There was a paper released by Matt Genge recently looking at the fusion crust, which is the outer layer of the meteorite that forms as it's burning up through the atmosphere, of a meteorite called the Winchcombe meteorite. And he actually used some of the images and the videos of the Winchcombe meteorite as it was entering to understand what kind of processes were happening as this meteorite entered the atmosphere.
I mean, based on the composition of the streak of light, as in the way, because different elements would produce different...
Yeah,
I mean,
for that you would have to be pointing something like a spectrograph at it, which would be very difficult. But you can look at like pulses of light, for example, to work out what's going on.
And so that leads us on nicely then to the types of meteorites. So there are three main types. We have iron, which are from the cores of asteroids and composed of iron and nickel. And they formed in the early solar system, the decay of radioactive elements produced heat, which melted asteroids, and the dense iron sank to the core to produce this sort of metallic core. And that's similar to the cores of rocky planets like Earth, Mars, Venus, Mercury. And then you have stony iron meteorites, which are equal parts iron and nickel, metal, and silicate minerals. And silicates are a really common group of minerals. So we have olivine, pyroxene is another. And these stony iron meteorites also contain precious gemstones. And our last type is stony meteorites, and these are the majority of meteorites that are found.
Yeah, absolutely. So the irons and the stony irons that you've mentioned there, these are going to be called our differentiated meteorites. So these are meteorites that have kind of undergone some kind of processes on their parent body, as you say, to form this iron and nickel. And these also include achondrites. So achondrites can be meteorites that represent partial melting or melting. So a lot of the Martian meteorites formed from like sort of maybe volcanic eruptions, for example. We get basalts. And so these are our achondrites. And then we've got our chondrites, which are our stony meteorites. So these are meteorites that haven't undergone any processes on their parent bodies. They've just basically been sat there since the solar system formed, which is great because they represent really primitive compositions. So kind of they form directly from the solar nebula and show us kind of what things were like in the early solar system. And our chondrites are particularly interesting because some of them contain a lot of water. So this can be up to about 22% weight water content. So this isn't just like water sitting in pore spaces. This is normally water locked up in sort of hydrated minerals like phyllosilicates. So these are just clay minerals.
So these are just minerals that show evidence that water has been there and altered these minerals?
No, that there is
water.
That and that there is also water in them at the point. And the particular ones are the Ci and the Cm chondrites. C stands for carbonaceous. They've got lots of carbon in them. The second letter is used for the group and is based off the name of a meteorite in that group. So an interesting one is the Winchcombe meteorite, for example. This landed in the Cotswolds a couple of years ago, and a paper released by Helena Bates and a team at the Natural History Museum in Meteoritics and Planetary Science this year showed that Winchcombe has 11.9% water content. And Winchcombe was particularly good because we picked it up very quickly after it landed, so there wasn't much time for rainwater to have its effects on the meteorite.
So we're talking about meteorites with a lot of water in them. Is that how... So I think that's how water came to Earth, or it might be part of how water came to Earth?
Yeah, so it's possibly thought that actually meteorites might have been able to deliver most, if not all, of the water to the early Earth, which seems crazy because in and of themselves it doesn't feel like they have much, but actually there is a lot of water locked up in these minerals. And that kind of leads on to another point, that a lot of these meteorites, particularly the carbonaceous chondrites, they've got a lot of carbon in them, and sometimes that carbon is present as organic molecules. And so there's this theory called panspermia, which suggests that life originated from outer space, that it didn't form on the Earth itself, that it came from elsewhere. And this would be supported by the presence of organic molecules on meteorites being delivered to the Earth. Now, it's not a foregone conclusion because we need certain types of organic molecules to create life, and there's really interesting chemistry in that we can get into another time. But it's a theory, and it's a plausible one, and it just shows why it's so important to understand meteorites and everything, all the rocks that we have out in space. But that's not the only reason why it's important to understand them, because actually they can pose a threat to us, right?
Yeah, well, I mean, one that destroyed the dinosaurs was 9.6 kilometres, and that was obviously incredibly destructive. And then you have one that was the size of Mars that smashed into Earth and formed the moon, ended up forming the moon. So there's somewhere in between there that would destroy the planet, or destroy humans.
Yeah.
And the question is, what would we do, or what can we do, if something like that is heading towards us? And there is one. So apparently there is an asteroid that is heading towards us and is due to hit Earth on Valentine's Day on 2046, according to NASA.
That's a nice little target.
You've seen that movie?
Day.
It's like, you see the moon? I'll throw a lasso around it, pull it down for you. It's like that, but it would just be a fiery ball heading straight towards you. But a recent BBC article spoke about the DART mission, which was developed by NASA, which sent this probe, the size of a refrigerator, to an asteroid called Dimorphos.
Yep, so Dimorphos is actually a little satellite of a larger asteroid called Didymos.
Okay. It's a satellite as in it's a...
Natural satellite.
A natural satellite.
So I guess like a moon.
Yeah, okay.
Of the asteroid.
But they were proposing they were talking about a sort of a kamikaze method where they would crash this probe into the meteorite and in itself would be destroyed, but it would knock the asteroid off course. And by course, what I mean is it was orbiting a 780 meter wide asteroid, which you just
Didymos.
said, Didymos, which takes 11 hours and 55 minutes. And now it's been slightly altered by this mission, by this probe, to 11 hours and 23 minutes. So it's half an hour.
And obviously there are so many factors that can affect this, like the composition of Didymos and the composition of Dimorphos and all sorts of other things. And this happened in September 2022, and I know that scientists are still analysing the data, trying to work out kind of what the effects are from this and how effective it is as a planetary defence mechanism.
Yeah, I mean, I think it only knocked the meteorite off course by tens of meters, which is tiny, obviously. But if it was heading towards us, a minor change over thousands and thousands of kilometres would actually be huge.
Yeah,
would actually be huge. And incidentally, I had a friend's Viva a few months ago, and I was chatting to this guy.
Final exam, right?
For a PhD final exam, you have a Viva and you spend 3 or 4 hours getting quizzed on all about your PhD. And if you answer the questions well and your PhD's good enough, then you become a doctor. But I was celebrating the fact that my friend became a doctor. And I was chatting all about the DART mission. I was getting really excited about it because I was explaining to this guy, like, you won't believe it. It's unbelievable.
Yeah.
And then turns out the guy I was sitting opposite had developed some of the mathematics for the actual probe mission by NASA. I was so embarrassed. I definitely got it wrong. But shout out to Tom Davison, Dr. Tom Davison.
For all those...
for the incredible work.
Yeah. I mean, it's crazy, isn't it? Like,
out of this world, you could
maths,
say.
Nice.
Yeah.
Yeah.
But the maths. I mean, I had tried to read some of the stuff about it, and the maths is incredible.
Next level.
Yeah. So that's it for our episode on meteorites. Thank you so much for listening.
And a little final word of advice. If you think you found a meteorite, there's loads of websites that can help you work out if you have, but I would suggest don't touch it with your hands because our hands have lots of contaminants on them. Pick it up with a clean glove and put it in aluminium foil. And then you can get in touch with your local university or a museum and try and work out what it is.
Thanks for joining.
Bye.